In this lesson, we will find how the flywheel is used to provide a uniform motion to the cutting blade while it is cutting materials. What property of the flywheel is most important for this use? How can we determine a value for this property? And why is most of the mass of the flywheel located near the flywheel's circumference? If a torque is applied to a fan blade initially at rest, its angular speed rotation begins to increase. Which properties of the fan blade do you think affects the angular acceleration the most? And how can we determine a value for this property? Consider a rigid body with a center of mass at G. It is free to rotate about the z-axis, which passes through G. Now, if we apply a torque T about the z-axis to the body begins to rotate with an angular acceleration alpha. Torque T and alpha are related by this equation. In this equation, I is the mass moment of inertia about the z-axis. The mass moment of inertia of a body is a property that measures the resistance of the body to angular acceleration. This is similar to the role of mass in the equation F equal to ma. The mass moment of inertia is often used when analyzing rotation motion, mostly in dynamics problems. Consider a rigid body and the arbitrary axis P shown in the figure. The mass moment of inertia about the p-axis is defined by this equation, where r, the moment arm, is the perpendicular distance from the axis to the arbitrary element dm. The mass moment of inertia is always a positive quantity and has a unit of kg times square meter or slug times square feet. Just as with the mass moment of inertia for an area, the parallel axis theorem can be used to find the mass moment of inertia about a parallel axis z, that is a distance d from the z prime axis through the body center of mass g. The formula is Iz equal to Ig plus m into d square, where m is the mass of the body. The radius of gyration is similarly defined, k equal to under the root L by m. Finally, the mass moment of inertia can be obtained by integration or by the method of composite bodies. The latter method is easier for many practical shapes. Let's consider this example in which a pendulum consists of a cylinder rod with a mass 10 kg and a sphere with a mass 15 kg, and we are asked to find the pendulum's mass moment of inertia about an axis perpendicular to the screen and passing through point O. Now, by following steps similar to finding the mass moment of inertia for a composite area, thus the wheel can be divided into a cylinder rod and a sphere. The center of mass for a rod is at 0.225 meter from point O, and the center of mass for a sphere is at 0.55 meters from point O. The mass moment of inertia data for cylinder rod and sphere are given on the inside back cover of the textbook. Using those data and the parallel axis theorem, calculate the following. According to the parallel axis theorem, I naught equal to Ig plus m into d square. Ig is the center of mass for the composite body. The mass moment of inertia for the rod is equal to 0.675 kg times square meter, and the mass moment of inertia for sphere is equal to 4.598 kg times square meter. Now add the two mass moment of inertias about point O. We get the mass moment of inertia for the composite body 5.27 kg times square meter. Thanks for watching.